Panda, the Ohio State University. He's a professor over there and is a distinguished scholar of computer science and engineering at the Ohio State University. He's published over 500 papers in the area of high-end computing and networking. The libraries that he published in the area of MPitch2, OmniPath, iWarp, Rocky, EFA, it was designed and developed by his research group. I mean, Hari, we heard from him earlier in the conference. We're going to hear from him later today. But his research group has done all this work, and it has been used by more than 3,100 organizations with over 1.2 million downloads. So he's causing quite a bit of adoption here. So this software is empowering several InfiniBand clusters in the top 500 list. I think he achieved the 4th, 8th, 12th, 18th, and 19th ranked ones. It's being adopted there. The RDMA packages for Apache Spark, Apache Hadoop, and Memcache together with OSU HIBD benchmarks from this group are also publicly available. So it's my pleasure to invite Dr. Panda, who is also an IEEE fellow, by the way.
Hi, can you hear me?
Yes, we can.
Okay. So thanks, Dibya, for the kind introduction. As you know, I am from the Ohio State University. This conference last year, they tried to have it here as well as this year, but we couldn't really meet physically. Might be next year, the third time will be a charm. So we'll be able to meet in person. So today I'll be talking about, this title is Efficient MPI Offloading Designs for Modern BlueField SmartNICs or the DPUs. So this work has been done by my team, two of the PhD students, Mamji and Nick, and of course, Hari, my colleague and research scientist in the team, is also involved here. So as many of you know, I mean, when we are talking about high performance computing, we are always performance. Okay, we want to deliver the best performance. And at the same time, we need to cut down on the overheads. And especially in this talk today, I'll be focusing more on the non-blocking communication, collective communication. I believe in this community, many of you must be knowing it. If not, the whole idea, like let's say you take a collective operation, like an all-to-all, all reduce. You know, these are being very widely being used for HPC applications and also in the modern deep learning, machine learning applications. So we want to do it at with the best performance. But sometimes, let's say you try to do all-to-all on a very large scale system, it takes a lot of time. So the processors are just waiting for the operations to finish. So this is where MPI Forum introduced the concepts of non-blocking collective. So the idea is that you initiate the operation like an all-to-all, but then if you have some other work to do, then you can go ahead and do that work and then come back and then check if the operation has been done or not. It is just like our regular life, you know. I mean, if I have to do some laundry, I just put the laundry and initiate that laundry. I don't have to wait there to see whether the laundry is being done or not. I can do my work and then check things. So this is where, in that context, we'll try to see, we want good communication latency, good bandwidth, of course, minimum contention for host CPU resources to progress the collective. So this is the problem happens, even though I initiate the collectives, who progresses them? Because collectives, typically what happens, if some of you would have designed, like I may need to send it to you, you may need to send it to somebody else. So there are all different kinds of algorithms, binomial, scatter destination, exchange. So the question is how I progress these collectives. If the processor again gets involved, then it is no longer non-blocking, or even though if it is a non-blocking, you may not get the best overlap between computation and communication. So that is the kind of the scenario what we are trying to study here. So people have done this CPU-based non-blocking many years back. A lot of papers have been published, including our group and many other groups, and solutions are also there in all other MPI stacks. But then what happens, if the CPU-based non-blocking communication progress takes place, it leads to subpar performance, okay, because the main application has now less CPU resources. Some people do this progress by using an additional thread, or some people do by providing some dedicated cores. But anyway you do it, you are basically taking out some CPU resources for making progress on these non-blocking collectives. So this is where the question comes, can we try to do this in an intelligent manner? Or can the network offload mechanisms be helpful here? And and in this context, we'll try to take a look at the BlueField smart NICs. It was identified as smart NICs. Now the name has been changed to DPU units. So I'll use both these terminologies in an interchangeable manner. So the focus will be, can we exploit these additional compute capabilities of the modern BlueField smart NICs to have these non-blocking operations to deliver peak pure communication performance, as well as for to get a good overlap of computation with communications. So now if you take a look at the smart NIC architecture, this is the BlueField. So we have a set of processors, and then on the BlueField, we have set of ARM cores. Okay. So now think of, I'll try to bring a easy scenario, like just like we work in an office environment. You can think of these processors are like executives, and let's say these ARM cores are like secretaries. Okay. So think of a group of executives have a group of secretaries. So how we can take help from the secretaries to make progress in some of the tasks. In this case, it will be non-blocking collectives, but might be in a regular business world. I mean, the secretaries are helping us to put together reports, budgeting, conference calls. So the idea is very similar. Okay, so we just have to orchestrate or these ARM cores properly with the processors and see whether we can get that kind of an overlap between computation and communication while giving the good performance. And yesterday we had a talk, I think in the same context, we heard about the storage. So here we'll be focusing mostly on the MPI and the non-blocking collectives. So in this case, I'll just briefly introduce. I think Dibya mentioned this. Might be many of you in this community are aware of this. This work has been done in the context of MHAPIS 2 project. So this project we started almost 2000. When the InfiniBand standard was announced, October 2000, almost now 20 years back, we were the very first ones to jump in. Prior to that, we are working on Myrinet, Quadrix. So we're the very first one, and in fact, the very first open source version of the MAPIS 2 library was announced in Supercomputing 02. And then since then, we are continuing on these. We started with InfiniBand, but now it has been extended. The designs have been extended for Omnipath, Rocky, even AWS EFA, provide support for all different platforms. It supports the latest MPI 3.1 standard, and will be quickly migrating to the MPI 4. And currently is being used very widely in a lot of worldwide, all different countries. And just from our website, we actually crossed in 1 million download last year. So we are steadily rising there, and we have been enabling a lot of top 500 clusters over the years. And our software stack is also available in all Red Hat, SUSE, OpenHPC, and SPAC. So this shows the overall MAPIS architecture. At the bottom, we support all these modern networking technologies. As the newer technologies comes, we take advantage of all the different transport protocols, interconnect features, HCI features, and now we are trying to take a look at this BlueField. And BlueField is one first instance, and I know other vendors are also working on smart NICs. We are working with some of them, and in the near future, you will also be seeing some of these solutions. And our research basically focuses on this middle, coming up with the good runtime, and then we link it to the MPI, PGAS, hybrid MPI plus PGAS, and also we have enabled the deep learning applications to go through MPI. So in fact, today also there is a Stanford conference taking place in another 2 hours. I'll be giving a talk there, trying to show how our MPI-driven approach can be used for deep learning, machine learning, DAST, a lot of next generation middlewares. So now let's try to go into a little bit more deeper here. So as I indicated, like if we take this executive secretary approach, so now we have this non-blocking collective operation. So we need to offload to a set of worker processes. Okay, so and BlueField has different kinds of operating modes. So here we have set it to separated host mode. and then the worker process are spawned to the ARM cores of the BlueField. So just the main process just spawn, give some task to the ARM cores. And then once the application calls the collective, the host processes prepare a set of metadata and provide it to the worker processes. And then that metadata has a lot of information, and it tells the ARM cores how to do the next set of steps. It's just like the executive is giving a set of instructions to the secretaries. Okay, so that's what we are trying to do. And then these worker processes progress the collective on behalf of the host processes. And then finally, once the message exchanges are completed, the worker process notify the host processes about the completion of the non-blocking operation. Again, very similar to that executive secretary model. Once the task get done, might be the secretary just goes back to the executive saying, yeah, this conference call has taken place, this report has been submitted, kind of things, so that the processor is mostly free to continue the processing. So go into a little bit more detail. So this is what trying to show an abstract concept here. So if we have the node A and the node B, we have the host memory here. So this is the BlueField DPU. So here we have the ARM. So we can think of like a exchanging information from the host to the SmartNIC. We can use an RDMA read. I indicated earlier, we configure it into the separated host mode. In fact, if some of you would have worked on KNL architecture earlier, it's very similar to that, like the KNC, KNL. So from the system perspective, this BlueField looks like a separate node. So then I can actually communicate. All my RDMA communications are available with me. So I can do an RDMA read, and then actually I can now do a direct RDMA write to the host memory of another node. Okay, so in this case, this is where we see like we are offloading. So we are offloading something here, and then the ARM processor can actually try to take care of whatever things we ask or orchestrate the ARM processor to do. So that is the kind of a broader, very high level idea how we are offloading things to the NIC. But now let's take a look at one of the concrete algorithm. So here we'll be talking like an all-to-all, non-blocking all-to-all. And as many of you know, I mean, all-to-all again has different kinds of algorithms. And here we'll especially focus on medium and large messages, because this is where we want to exploit the overlap. If it is small messages, it is getting done very quickly. So there is no point in overlapping computation with communication. If it is for medium and large messages, it takes a lot of time. And this is where we want to offload and try to get the overlap. So here, if you see in the first step, as I showed earlier, like this is trying to show, let's say I have 4 processes and let's say 4 worker processes. Okay, so think of again 4 executives and 4 secretaries here. So we are able to like first do this RDMA read. So that is like a step 1. And in this case, we are considering a scattered destination. Okay, so that means everybody gives the data to their worker processes in the BlueField DPU, and then they are actually doing an exchange. So in this case, in the step 1, in the step 2, everybody can write to their, let's say, +1 neighbor. And then in the step 3, they can write to +2 neighbor, +3 neighbor. So like this in n steps, everybody will be getting the data. Okay. So as you can see, after we do this offload, which actually this ARM core is trying to do, it's an RDMA read. Okay. So the processor is not involved at all. And in all these other steps, the processors are also not involved at all. So that means we are totally trying to get the maximum overlap, or totally detaching what the ARM cores are trying to do from what the processors are trying to do. And then of course there is some overhead and all. We have worked with BlueField 1, BlueField 2. I'll show the results with the BlueField 2. I think over the each generation, I think some additional things are coming. And so then in this case, we also take care of like a message chunking, pipelining. These are the very standard mechanisms which get used, so that we need to balance the overheads of this kind of orchestration, so that we get the best performance and best overlap. I think some questions are coming up. Let me finish this, and I'll be very happy to answer these questions. Okay. So this is where we have done this experiment. So this is from the Mellanox NVIDIA HPC Advisory Council, HPC Center. So it has a cluster with 32 compute nodes. So this has the on the CPU side, this has the Broadwell series of Xeon, and then the BlueField 2 DPU has SDR100. It is a ConnectX-6 SCA, and this is the OFED version. And then the BlueField 2 has actually 8 ARM cores, but they are only operating at 1.9 gigahertz. Okay, so we need to keep this in mind. Just like in the real life, we see executives and secretaries based on the capabilities, based on their qualifications. Executives has much more capabilities to do for certain operation, in this case like a compute operations. So the ARM cores need not be very efficient in totally offloading the compute, but here we are trying to offload the communication. Okay, so that is a little bit different aspects. So then we took our MVAPIS2 library and we have done this design. And also many of you must be familiar with the OISU micro benchmark that we have been doing again for 20 years. It has already support for non-blocking collective. So we use that standard to evaluate all to all. And we also have a P3D FFT application. So I'll try to show results from both. And just like people have different number of host processes per node, in the community people call PPN, we also introduced a terminology called WPN. It is a number of worker processes per SmartNIC. Okay, so how many of them are using? Again, it is a collective operation. So might be it has 8 ARM cores. We can use 1 or 2 or 4. I'll show results with a different number of cores just to see the trade-off. And then the OISU micro benchmarks, if some of you are familiar with the non-blocking collective benchmark, let me explain. So we introduce something called a pure communication latency. That means is the latency T is measured. So you call MPI all to all, I all to all, followed by MPI wait. Okay. So that means we are not doing any other things, pure communication. But that is not the whole idea of the non-blocking. The non-blocking idea is to really add compute there. So that means I initiate I all to all, do some compute, and then wait. So we also have that provision in our OISU micro benchmark. So we can add some synthetic compute, and then that synthetic computation is also a parameter which is like similar to like what you can get from the latency. Okay, so the thing is, if I can have the 100% overlap, so then I should be able to, if it's taking some fixed amount of time for the non-blocking, I should be able to exactly use that time to do similar kind of computation. And that's how we compute the overlap as a percentage. If I cannot overlap everything, or I can only only do half of that, then the overlap will be 50%. So this is a part of the standard benchmarks. You can take a look. The code is public for many years. So let me then go into some of the experimental numbers. So the first we try to see the overlap of computation and communication. So what we are trying to show, so this is on 32 nodes, 16 ppn, that is on the host side, and the right hand side is 32 nodes, 32 ppn. So it has 32 nodes. We are evaluating in 2 different modes. And then these bars there are 4 bars. So this is the basic MVAPIS2. And this is BlueField to ConnectX CXCA. So we are not doing any offload. So the adapter is just performing the basic communication. Okay. So we are not taking advantage of any of these ARM cores. So that is the this line, the light blue. So then these 3 bars are trying to offload, and we are using increasingly different number of worker per node. Okay. Because it has 8 ARM cores. So here we are using 1 versus 2 versus 4. Okay. So as you can see here, especially in these medium message sizes, when you are trying to do this progress, so that is the basic thing, whatever is available in the basic MVAPIS2 without any offload. So you can see that the CPU are still busy up to certain fraction. You get good overlap like a 98%, but on the right hand side, especially for large messages, we almost get like a 100% overlap here. So that means the host has given things to the ARM cores, and then we are able to get the peak overlap. So now let's try to take a look at the pure communication latency. So here again, like there are 4 bars. So especially if you see, this is like we are starting with a 16K medium message size to 512K. And then here also same 16K to 512K. This is for 32 nodes, 16 ppn, 32 nodes, 32 ppn. So here, if you see, like this is the best, this is the pure communication latency I indicated. That means I just initiate I all to all and then MPI wait. That's all I am doing, nothing else. And in that case, with the offload design, if you just measure that, there is some overhead, okay? But the 1 ppn there is a lot of overhead, but as we go into start using 2 workers or 4 workers, it comes closer to this one, okay? So we are able to deliver on par performance. It is not like a twice slow or 4 times slow kind of things. But what it shines here in this slide is that when we add the compute, okay? Because when we add the compute, that is the whole idea of the non-blocking collectives. This is the way it needs to be used. So now if I add the compute, now you can see the light blue bar where pure host is trying to do, it initiated the non-blocking, it is trying to do the progress, but at the same time, it is trying to do the compute. Obviously, the cost goes up quite a lot. But on the other hand, these offloaded designs with 1 WPN or 2 or 4, as you can see with 4, we almost get like a 44% benefit in the total execution time here. And then in this case, here also we get like a 36%. Okay, and it varies based on the message size, just like any other application we see. The benefits differ. So then we tried to do we took this P3D application, P3D FFT. FFT is a very common application, as you know, is very commonly used in a lot of kernels. So there is a standard version P3D FFT, and we converted that to use non-blocking all-to-all. Okay, so that is the benchmark we are trying to use here. And so that means it is doing the P3D FFT, but in a modified application where we do the non-blocking collective call, but we are still computing and then come back and then check. So that will be the best scenario of using the non-blocking collective and the offload mechanisms. And here you see like a grid size for different grid size. So this was again 32 nodes 16 ppn and 32 nodes 32 ppn. So here you can actually application level. In this case, you can get actually 15% or 25%, 30% benefits kind of things. And that actually shows the real capabilities of this DPU processing unit. So these are some of the initial results we have. We have actually a paper accepted for ISC 21. So there will be actually presenting a lot of detailed results. And with this, let me conclude here. What we have shown here in this work is that this new generation of the smart NICs or DPUs are coming up. So the question is, how do we take advantage of that to design the next generation API library? And our first step has been this non-blocking collective. And I try to show that especially with I all-to-all, which is the most dense communication pattern, we are able to demonstrate 100% overlap of computation and communication while having on par pure communication latency. And also for a P3D FFT application, we are able to show like almost 1K processes. We are able to gain benefits by 30%. So we are actually working on other non-blocking collective operations. As you know, the collective, there is a large set. We'll be going through gradually one of them earlier, one after another. And also, we are also trying to think in a very similar manner to offload some of the things, point-to-point communication. So those were the kind of on our roadmap. And as these solutions are available, just like what we have done in the last 20 years, you'll be seeing these kind of solutions being available in our MFP2 releases so that you can actually try to utilize that for your applications. So with this, let me stop here. These are all my web pointers, and I'll be very happy to take questions.
There's a question from Glenn. Are we bound by the L3 cache line on DPU or number of WPNs based on cores plus core frequency?
Yes. So let me go back here. So as you can see, we have not done the cache analysis more, but here we have done the number of cores. So as you can see, this worker per bone, like with 1, we get some benefits, but not much. But after 2 we get very good benefits. But between 2 and 4, you see there is not much benefit. So it will depend on your collective, your characteristics of your message sizes. So it'll need a thorough study. We have not done that yet. Does that answer your question?
Divya, can I go?
Yeah, go ahead, please.
Yes, thank you.
Nice presentation. I was just wondering if some of the semantics that you talked about earlier with the metadata that was going to worker threads, and some of those concepts there. And I'm just wondering, is there a plan to like take some of those concepts if they're not already in the LibFabrics API and get them there?
Well, we have not looked at that angle yet. We have not looked at that angle yet. This is purely, we are just trying to, this evaluation was just done with the Mellanox Offload, whatever the APIs have been provided. And it is a separated host mode. So we just use the basic RDMA operations between the host CPU and the ARM CPU.
Right.
Thank you. There's one more question here. From your experience, Dr. Panda, what changes would you like to see in the future SmartNIC design to expand the capabilities?
I mean, again, this is like just like as I said, if I take this executive secretary approach, I always tell that to my students. I mean, if I can have a secretary with a PhD degree, but not costing a much, I can offload everything, am I right? I can ask the secretary to write a proposal to get the money, do the research, write papers, submit the report, and just put my name there, right? So that's what we want. I mean, of course, offloading a lot of things will be very challenging. It will also be expensive, but whichever vendor can come up with the best design in the next few years, I think that's what we'll win.
Thank you, Dr. Panda. Any other questions?
Yes, this is Glenn Church.
Please
Hey, I had a quick question. Have you tested Sharp versus DPU, and do you think there's some value in enabling Sharp for this type of solution?
Yes, we have not done that, but those are the next steps. I mean, we have, like, in fact, in the next talk, Hari will be providing results on the SARP. That is the next talk. After the break, we have very interesting results with SARP in network computing. So now these things, now you need to see how the in-network computing SARP can be also combined with the DPUs. We have not done that yet, but those are on our roadmap. Yeah.
Thank you, sir.
Thanks.
Do you know what the latency overhead is of using offloaded collectives to the SmartNIC, the BlueField SmartNIC?
Can you be a little bit precise, Mark?
So say for a small collective, you're correct in that offloading something that's small doesn't sound very interesting, but
Yes.
there can be a lot of skew across all of the processes that are contributing to the collective, right? So you've got an all reduce across tens of thousands of ranks, and they all arrive at different times. So being able to do that in the background can free up your compute in the same way to, run floating point on the CPU. So what's the latency for small collectives?
I don't have anything top of my head, but I can send you a note.
That would be great. Thank you.
Yeah.
I know, Dr. Panda, you have a class at 9 in 5 minutes. So I'll ask one last question.
Sure.
Do you have plans on using the embedded CPU function ownership mode?
Of the DPUs, you see, it depends. Like, especially for MPI, we started with this self-hosted mode. But if you want to do some kind of additional packet processing while the data is in transit, we can use that other mode. But we have not explored that yet.
Yeah. All right. Thank you. So I'll let you go to your class now. Thanks for staying on late and supporting OSA.
Thank you. And as I said again, hopefully next year, looking forward to seeing all of you in person.
Yeah, Hari promised a free tour. Yeah.
Yes, we'll be very happy to show the campus and the lab and the universities. Okay.
Cool. Thank you.
Thanks. Bye.